Okay, so I'm very glad to be speaking for a second time. Today I will speak for my collaborator Isha Kotecha. She's a PhD student at Albert Einstein Institute, and we're working together with supervisor Daniele Oriti on this project, which is still kind of a speculative project, I would say. So again, I will try to convey the message without entering too much into the technical details, and which many parts we don't control yet. So, so the talk is about generalized Gibbs ensemble in discrete quantum gravity. So the point is, avoid giving you an introduction on quantum gravity, especially in the case of loop quantum gravity, so background-independent approaches to quantum gravity, to get in medias res to the message and to the approach, somehow to the idea. So this is the outline of the talk. The tentative outline is basically I will start, given a lot of information we had yesterday, today about group action, reduction by group action. I would like to link this topic to that sort of arguments. So I will show you basically what is the role again played by the momentum map in this game. I will show you how simplicial geometry can be considered as a peculiar case of a constrained system. Not that peculiar actually, but it's very nice to see that, because as a constrained system, in particular as a symplectic manifold, then can be quantized, and this is basically the starting of the quantization of geometry, which is the core of loop quantum gravity or these kind of theories. And so then I will introduce this probabilistic approach, which I will show you what I mean. So kind of a probabilistic approach to symplectic reduction again. And I will close with introducing, so tangentially, this notion of quantum many-body geometry. So a collection now of quantum simplicial geometries, which can be described in terms of quantum many-body systems, and again, whose partition function would, eventually give you in perturbative approximation Feynman diagrams, which are supposed to model, say, quantum geometries. So it's very involved. That's why I want to be very, very simple. So let's start with the symplectic reduction by group action. So this is everybody, I think, knows this. So we consider a smooth symplectic manifold M, which constitutes typically the extended phase space of some given system, and an Hamiltonian function and some group of symmetries which acts on this symplectic space. This define basically my system, typically mechanics. I consider action of the group, which is Hamiltonian, so strictly symplectic, a symplectomorphism. I construct a momentum map associated to the Hamiltonian action of this group on my manifold, on my symplectic manifold, and yeah, defined as like a map from the manifold to the dual of the algebra associated to the group I'm acting with. And this is the definition. Basically, this is a co-momentum map, so it's the pairing between the Hamiltonian function associated to this action, which I call F, paired with the element of the algebra, so the vector in the algebra X, which is then realized in the manifold in a specific representation as a vector on the manifold. So now the interesting thing is that what we typically, like a Dirac standard approach to reduction, to symplectic reduction, can be done in terms of momentum map. So what's the point? The point is that if I fix if I fix the value of the momentum map and I look at the inverse image of this value of the momentum map, this is a submanifold of the original extended phase space, which is basically the manifold where all the orbits which commute with, which are invariant with respect to the symmetry of the symmetry. So the action of the group which I'm considering are lying. Okay, so this is basically an immersion, so a restriction to a submanifold where invariant configuration in my extended phase space live. So typically this is a starting point for quantization, because then I would quotient by the isotropy group, the group of yeah, let me say. So let me So I consider then a constraint system in general as being characterized by the system itself times some group, which is typical. This is interesting when the group is known a priori. So you can bypass basically the information which is in the Lagrangian and some momentum map. Okay. So now, as I was saying, so if G mu is the isotopy group of this submanifold, by equivariance of the inverse image of the submanifold itself, basically under the group, the isotopy group, we get something which is not. So that group was a presymplectic, if you want, has a presymplectic structure associated with it, and the quotient has now again a symplectic structure, and this quotient is nothing but the manifold of motions or the actual physical phase space of the system. This is a standard reduction by group action. So let me consider now a very simple example of this, a very trivial example, but which will be interesting for us. So consider a bunch of vectors in R3. Okay, so these vectors you can think of them associated to a sphere S2 in R3. This collection of spheres is itself a symplectic manifold, right? Because of the symplectic nature of this two sphere in R3. Now, consider now the action on this collection of spheres. Now, the action will be a diagonal action, so I act with the same group on all of them. And so the corresponding momentum map will be a sum of a momentum map restricted to the single sphere, and is given simply by the linear momenta, so by the vector themselves in this case. So it's a sum of vectors. So it's a sum basically of these vectors that we were considering before sparsely in R3. But now what I can do is fix again the value of the momentum map to be a specific value. Here I want to fix it to be 0. And this corresponds to a very well-known condition, which is the closure condition, or a Gauss, if you want, constraint, which tells me that basically all these vectors are summing to 0 in space. But this defines a very specific configuration, and especially, I mean, these vectors, they don't need to be, I mean, you are not specifying like them on a plane, so actually we want them to be non-coplanar. So if this is the case, there is a known theory by Minkowski, a beautiful theorem, which tells us that if the unit vectors are non-coplanar and their areas, so there are positive numbers such that the closure condition holds, then there exists a close, which is just a mistake, polyhedron whose face have outwards normals Ni and area Ai. So basically, I gave you a collection of closed vectors, non-planar in space, in R3. You can dually think of these as a polyhedron, where each vector is now a flux associated to a face, and the area of this vector is basically the area of the face itself. So any polyhedron, every polyhedron can be modeled in this way. And so basically, a simple constraint on this very simple symplectic manifold then gives us basically simplicial geometry. So the nice thing is that a simplicial geometry can be considered as like a dynamical constraint system. In this case, there is no dynamics. There is just a constraint. But this is not a trivial case because, for example, in general relativity, you don't have any dynamics. Hamiltonian is 0, and you just have constraints. So general relativity is a fully constrained theory which describes the full space-time, let's say. This is a trivial, say, model which defines a tetrahedron. Okay, but it's still geometry which emerges in this sense. Okay, so this is what I was saying. So imagine these are non-planar, then this is a dual picture, okay? Okay, so this comes the most speculative part, about which I've already kind of told yesterday. So let's say that we have a lot of these vectors in space. We want to consider a situation, especially we will look at quantum states. So we imagine that we have an ensemble of these vectors. So when you have graphs, which is made of a lot of nodes, a lot of vertices, or if you want a lot of geometrical configuration, it's really unfeasible to think of constraints to act in a strong way, in a hard way. Many times, we want to consider a statistical, like a statistical approach to this. So many times we consider, and this is also the case in field theory, for instance, when we have like a gauge field theory and the volume, the moduli space is given in these terms, so in terms of some projection on some submanifold, basically. So what we want to do is to think of a constraint in a statistical way. There are two ways to do that. One is to have a microcanonical approach, where basically you impose constraint in a strong way, so in an hard way, but still in a probabilistic sense. So you have an integral over the phase space, and you want to project via some delta, which basically is a redefinition of the measure, if you want. So you adjust summing configuration which satisfies some constraint, like in this case, the standard Gibbs state, microcanonical case, it will be a constraint on the energy to be fixed. Otherwise, you can consider a canonical ensemble, so a soft constraint. So in this case, you have something different. You want that the constraint is basically fulfilled on average, so you're asking for some average to be constant, and then by a Lagrange multiplier, by a rational approach, you end up having a Gibbs state. Okay. So in the second case, in particular, the constraints holds as ensemble averages, while individual simplicial configuration may violate them. So you have something which you want to look at it, you want to think that this is actually satisfying your constraint, but if you go into details, this constraint may be violated. It means that if I have a bunch of tetrahedra and I want to look at them, so a bunch of vectors, and I want to look at them 4 by 4 as tetrahedras, I may consider the fact that they won't close perfectly, but they might fluctuate, and having pseudo-convex, pseudo-closed configurations. So, so now that's exactly what I want to do. So so again, the motivation which I didn't give you is somehow based on quantum gravity, but I want to keep that secret till the end. So consider now the space of this closed polyhedra with a fixed orientation and extend the phase space description that I gave you before, that was intrinsic geometry basically, to encompass the extrinsic geometric degrees of freedom. So I want to give you like a space points and conjugate momenta. In this case, those objects were living in some vector space. I want to give you the dual. So it was SU2, the algebra, and I conjugate variables are variables lives in the dual of the algebra, and you can think of the algebra times the dual as parameterization, like trivialization, or if you want, of T star S2 to the n. There is a mistake here. Well, D would be the number of tetrahedra considered, or polyhedra, cross quotient by SU2. So this is basically the same object as before, where now S2 is replaced by SU2, and I'm quotienting a series of S2 by this group, which is S2. So I'm considering rotational invariant. SU2 is the complex covering, double covering of SO3, so I'm still considering SO3 invariant objects. So one object will live in this, so this will be the phase space, so the cotangent bundle, if you want, of a single tetrahedron when D is equal to 4, and I want to take the Cartesian product of these, so n tetrahedra, so n cotangent bundle, so again a symplectic space. Do you know the time? Sorry, when did I didn't notice when I started? 5 minutes. 10 minutes left. Okay. So I will be very quick. Yeah. So in this space, then what I'm envisaging is basically a system made of many classical or quantum eventually tetrahedra, which can be defined via constraints among. So what I want to do, I want to have a gas, if you want, of tetrahedra. So I want a gas of simplicial geometric configuration, and I want to define interaction among them, possibly, or minimal interaction via imposing some constraint. In the same way you do in in the Boltzmann approximation when you set constraints on relative distance as a contact interaction, for instance, so without adding extra dynamics. Okay, so this is a nice standard cotangent bundle. We can quantize the algebra, the Poisson brackets there. So we get basically, I skip the details, but we get a very nice L2 Hilbert space, which is basically the set of L2 function on SU2 and quotient by SU2. By Peter Weil, this is a compact group. You can see that this can be expanded into some of a irreducible representation of SU2 of spaces which are, because of the quotienting of SU2, are invariant space with respect to SU2 of products of irreducible representation of SU2. So if you want to use a basis, you can take a basis of Wigner matrices for each j. So I skip the details, but if you can ask whatever. So invariant on the SU2 of a set of say n say L H J L, where H J L is something like the product of the new J2, basically two spin particles, J bar. Okay. So you take the invariant, so you can think of it as projecting into the SU2 invariant subspace by group averaging, for instance. A basis in this space is given by the Wigner matrices, which are, for example, labeled by the fundamental representation times the element of the group and indexes which tell me, so these are indexes of the projections Jz, and J square is the Casimir of the group. Okay, so this object is basically telling me about the transformation of the group from some point to another. So I don't have time, but this is really the basics of how do you construct spin networks. Spin networks are basically, you can see spin networks are networks of these links, which are nothing but holonomies, basically, of some spin connection of the GR. Okay, so I don't want to enter in the details, but 5 millions. Okay. So okay, so I have this space. So this a basis in this space again is called intertwiners. So now my tetrahedra are basically intertwiners. So they became sort of projectors into this invariant subspace. So or maybe they can be written as a function in this space in terms of a basis, which is a composition of this basis of Wigner basis times some coefficients, which will be like a Clebsch-Gordon. Sorry, okay, coefficients. So intertwiners basically are projectors onto the subspace, sub-invariant subspace. Okay, so if there is time, I will go maybe more into details. If somebody asks, I will tell you what a spin network is, but we don't have time. So a quantum tetrahedron then is like a one particle into this one particle Hilbert space. Okay. So in particular, I have to take all the irreducible representation for that to be a proper Hilbert space in L2 of the invariant space. So, and then I take a collection of these. So I'm basically reproducing what I had before for the classical case. Okay. Now this is my setting. I can improve this setting by noticing that I have a bunch of quanta, and I can basically change basis and pass in a Fock space representation. So Fock space is basically a nice in second quantization, basically, it's a more suitable setting for describing a system, many-body system, if you want. So I'm assuming some statistics for these objects, and then I'm giving you basically imagine I'm changing base, so I'm passing it from a first quantization formalism to a second quantization formalism, and then I can write my Hilbert space for the full system as a Fock space. So if you want a direct sum of a system of 0, 1, 2, 3, 4, 5, 6 particles. Okay. Accordingly, basically, I will have to define ladder operators in my Fock space. I'm sorry, I will not be able to give you more details, but so what is the point is, in terms of these ladder operators, creation annihilation operators, I'm considering a vacuum and the quantum level, and these operators are creating or annihilating these tetrahedra. So now these tetrahedra are really like particles, which have an internal structure, but they are like particles. Now, these are tetrahedra, so these are quantitative statistical states are now given by density operators. So they are self-adjoint, positive, and trace class operators on this Fock space. Now, what I want to do is to define a Gibbs state, and this is the meaning of the title. I would like to define a statistical state of this quanta. Can I do it? Yes. Why? How I want to do it? Following basically the standard approach, but now considering again, like as an operator, which will end up at the exponential, a constraint or a set of constraints, which eventually will determine the behavior, so the configuration, so the energy, for instance, but not exactly the energy of this collection of quantum tetrahedra. So the nice thing is that you can define this object, you can think of it as a grand canonical system, and then if you choose a specific basis, like a coherent state basis, you can re-express this partition function in terms of these fields. And I have 0 minutes, right? Okay, I have to finish. And these fields basically, this leads me to a partition function which reproduce what is a group field theory partition function, which is let me say a generating function for models of quantum gravity. So you have a model of quantum gravity is something where it's a field theory, something which I give you. Okay, I give you because I know the Lagrangian. I want now all these approaches made to construct, to give a statistical justification to this field theory, if you want. So if I start from the minima, so for the minimal entities at the quantum level, I want to show that I can, from a statistical approach, arrive to a field theoretic description, which will be like a coarse-grained description, an effective description, which reproduce exactly what is what may be at the beginning of a quantum gravitational model. And so the comments is that, yeah, exactly what I was saying. So this is a starting point for any quantum gravity theory, not for any, but let me be vague here. This is what basically expanded in perturbative Feynman diagrams gives me what is called a spin form, so a connection of new graphs, which are dual to complexes, which we thought as which we think as realization of space-time geometries in discrete sense. Okay, thank you. Sorry for getting.
Very short.
It's not short.
I would be very short answer.
So just to be sure. So you are quantizing, SU2 is a quantization of the angular momentum, right?
Mm-hmm.
So you're creating quantized the object, and then you are realizing the operators in Hilbert space that realize this quantization. Is this correct?
Mm-hmm. Yeah, so I'm considering quantization of something more, slightly more, a collection of SU2.
Yes.
Quotient by something extra
yes, so
symmetry.
then you are realizing this in some Hilbert space also.
Yes.
As operators, right? Because it's spoke about ladder operators. Right?
Then, yes, in the Fock space, I'm realizing
yes,
this
so
as
my
operator.
question is like, okay, but each function somehow has nothing to do with the other one. So they are commuting. I was thinking, are you
exactly. They are like
commuting objects? Because there are also, fermions and so on. You are not considering those.
Exactly, no. So I'm considering just bosonic statistics.
Yeah.
But you can consider fermionic.
Must consider. Yeah. That's the next step.
Yeah, so the bosonic statistics is compatible with gravity because in fermionic case you have a strong symmetry constraint while and you don't have bouncing. I mean,
okay.
so.
Okay, I don't want. Yeah, but we'll continue.
There is a motivation for that.
Okay.
The discussion. Thank you again.
Thanks.
Thank you.